All right, welcome back. So last time we discussed distributive lattices, and so here's an example of a distributive lattice that I did last time. And last time I proved this theorem, which is called the fundamental theorem of distributive lattices, or Birkhoff's theorem, which says that every distributive lattice comes from a poset as its lattice of order ideals. So remember that an order ideal is just a downset of the poset, and then every downset of this poset has a unique element here that corresponds to it. So for example, if you want the downset 1, 2, 3, 5 in this picture, I mean the downset 1, 2, 3, 5 in this picture corresponds to a vertex here. That's going to be the join of 1, 2, 3, and 5. Right? So you look for the smallest upper bound of 1, 2, 3, and 5, which is this point right here. And so this is going to be 1, 2, 3, 5 in this picture. And we showed that you can go back and forth, and this is a bijection between distributive lattices and posets. Okay. And so I wanted to start today by discussing the following results. So it's a proposition. Let's say that you have a poset. Let's say it's finite. Let's say you have a natural number. Then the following things are equal. So 1, the number of order-preserving maps from your poset P to the chain of M elements. Right? So meaning that, I don't know, you have some chain of M elements here. Like maybe it's, let's see, what's the M that I want here? So maps from here to here, which preserve the order, meaning that if, for example, because vertex 2 is less than vertex 5, then you should assign to the vertex 2 a number less than or equal to the number that you assigned to 5. Okay, that's an order-preserving map from this poset to this poset. Actually, maybe we'll get a little bit less confused if we call this A, B, C, and D. Okay. So this is one of the things that we could count. Another thing is the number of multichains and what's a multichain? It's like a chain, except that you can repeat elements. In the distributive lattice J of L. Okay, so it's like a chain, except you can repeat elements. Right? So a multi-chain could be going from the empty set to this point, to this point, to this point, to this one, then you stall here for like 3 steps, then you go up here, and so on. It's a multi-chain. And the third thing is the number of elements of the distributive lattice of P times the chain of size m minus 1. Okay. So that's the proposition, okay? And I'm just going to do a proof by picture, actually. So what's A? Well, like I said, A is mapping the I don't know. For example, you might decide that I mean we're going to map P to this chain. So each one of the elements of P gets assigned one of the elements of the chain. Okay? So who gets A? Let's say, for example, that maybe these two guys get A. Okay? F of these two guys is A. Then who gets B? Well, for example, if I want A to get B, then I have to make sure that 5, which should get something less than or equal, should also get B. Right? And so maybe these guys get B, and maybe, I don't know, let's say that these guys also get B. Okay? And then we might say that nobody gets C. That's a possibility. I didn't say that this has to be surjective. Right? And then maybe these guys get D. Okay? And so A is just kind of taking your poset, okay, and just kind of splitting it like this into, I don't know, some of these guys get the value 1, some of them get the value 2, some of them get the value 3, and so on until some of them get the value n. Okay? Now, the thing is that this very naturally corresponds to a chain over here, right? Which is to say, okay, start with the empty order ideal. I have to, right? The first one has to be empty, and then I need to go out by order ideals. But then it's very clear what I should do. I should take the first order ideal is 2, 3. Okay, so 2, 3 corresponds to this guy right here, and then the next order ideal should be just, 2, 3, and then all of these guys, 1, 4, 5, 8. So where is that? 2, 3, and then I join with 1, I join with 4, I join with 5, and I join with 8. Yeah, so I get, so this was 2, 3. This is 1, 2, 3, 4, 5, 8. And then finally, okay, then what about the next step? I take the union of A, B, and C, right? And because C is not there, that means that the walk repeats and stagnates there for a second. Okay, so it goes to 1, 2, 3, 4, 5, 8 again. And then I go to D and I get everything. Okay? So this is kind of the same. And this is clearly bijective, right? If you start with a chain, then it's very clear how to reverse that and get an order preserved map this way. Okay. So this is the same thing as B. Yep.
So when you were doing the map from P to N, it's okay that here 2 and 1 are comparable, but in the chain.
So the question is it okay that
The order still
1 is less than? I see what you're worried. The number 1 is less than the number 2, and yet 1 got B and 2 got A. Is that a problem? That's not a problem because it's not about the labels. Actually,
no, I mean like comparing them.
Okay.
The level.
Remember, this is not about levels, right? So the first of all, 1 and 2 are incomparable in this poset, and the condition is that if you have elements that are comparable in this poset, then their images should satisfy the same inequality here. But because 1 and 2 are incomparable here, then you don't care where you map. But for example, you need to map 1 to something less than or equal to what you map 4. Okay, so this argument shows that A is equal to B. And now, to show that it's equal to C, I should show how this corresponds to an order ideal of the poset P times m minus 1. Okay? So this is meant to represent P. So what is P times m minus 1? Well, that's m minus 1 copies of P, right? So in this case, m is 4. And so I get 3 copies of P, right? And then 1 corresponds to 1, 1 corresponds to 2. Or let's say that 1 corresponds to, sorry, I also changed my mind about what I was going to do here. So actually I decided to call these A, B, C, and D, right? Now I'm going to consider the poset P times n minus 1, the chain n minus 1. And I'm going to do that by just dropping D. Okay, so that means that I get one copy of P corresponding to A, one corresponding to B, and one corresponding to C. Okay? But you should think that this is a product poset, right? And so here I have the comparabilities, but also I know that A is less than B is less than C, and each element here is less than the corresponding element here and here. Okay? So you have all these edges coming through like this. Okay? So how do I get an order ideal in this poset that represents this chain? Well, one way of doing that is by, actually I think I have this, yeah, I have this wrong here, so let's get it right. So really what I want is the opposite. So what I'm going to do is call this C, B, and A. And so here I'm going to take the union of the things that map to A, the things that map to B, and the things that map to C. Okay? And just look at all of this stuff. Here I'm going to take the union of the things that map to A and the things that map to B. And here I'm going to take the things that map to A. Okay. So in the first copy of the poset, I look at the elements of P that map to A, in the second one, the ones that map to A and B, and the third, the ones that map to A, B, and C. Okay? And so you can see that in each level, this thing is an order ideal, but also it's an order ideal in this direction, right? Because if you have anything over here, then you're also going to find it in the next level and in the next level. And so this is an order ideal of this product. Okay? Why did I not put D? Well, because D is always going to be the full poset, so that's not really adding any information. That's why I dropped it. Yep.
So what you said, it should be drawn kind of like that then? Like what's the ordering? Like what's greater than what?
I mean, really, it's just this poset, and I'm just kind of imagining that this copy corresponds to A, this one corresponds to B, and this one corresponds to C. But really, P times the chain n minus 1. I mean, I can just say this is the chain 1, 2, and 3. But in the back of my mind, I just remember that 1 corresponds to C, 2 to B, 3 to A. Okay, so that's the proposition. And let me make another proposition, which is that the number of linear extensions of P is the number of maximal chains of J. And it's kind of it's almost a special case of this equality from A to B. Okay? Because how does this go? First of all, remember what a linear extension is. P actually comes to us without names. Right? These guys don't have names. At least their names are not linearly ordered. Right? And then, what's a linear extension? A linear extension is a labeling of the elements with the numbers 1, 2, 3, up to however many there are, that increases as you go up the poset. Okay? And so I just erased one, but a different linear extension would be, for example, to say this is number 1, this is number 2. For example, I might say that this is number 3, right? That's not a problem. And this is number 4. Even though 3 is higher than 4, they're incomparable in the poset, so this is still a linear extension, right? So I might say this is 5, this is 6, this is 7, and this is 8. Okay? So in every edge of the poset, the labels go up. And now forget about this ABCD business, okay? But let's apply the same argument. Okay? So the point is that I can consider this as a function from my poset to the chain of 8 elements. Right? And so now that corresponds to what? To not these guys anymore, but to like, okay, first was this guy, right? And I guess I should erase the old names. So what is the chain corresponding to the linear extension? I say, well, this guy goes first, right? So I go from here to here. This guy goes first. Then this guy goes second. So I take the joint with the second element, which is this one. Right? So I land over here. Then third, I take the joint with this guy, which corresponds to this guy. Right? And so I land here. Then I take the joint with the fourth element, which is this one. So the joint of this and this is this. Right? Then I take the joint with the fifth element, which is this one. Then with the sixth element, which is this one. Then with the seventh, which is this one. And then the eighth, which is this one. And I get a maximal chain from the bottom to the top of the poset. Okay? And if you remember that these are order ideals, then all you're doing is just adding one element of the poset at a time, right? First you add this one, then you add this one, then this one, and you're just going up the order ideals. So the proof of this is the same. Okay. All right. So having done that, I want to talk about this number. So this is going to be denoted by E of P. The definition. E of P is the number of linear extensions. Okay? So if you want to count linear extensions of your poset, then you can do it here, or you can do it here and count maximal chains in J of P. Okay? And because J of P we saw is embedded in a lattice, right? Then we're really basically counting lattice paths in this grid, right? From the bottom of the grid to the top of the grid, we're just counting lattice paths through there. So this is kind of like some restricted lattice path enumeration. Okay. And so to practice with this stuff, I would like to suggest two exercises to you. What is the number of linear extensions of the two disjoint chains M and N? So I want you to think about that for a second. It might take more than a second, but it's not too hard to see that this number is exactly M plus N choose M. Okay? And then another one that I would like you to think about is, what if you take the poset 2 times n? So m plus n is a chain of size m and a chain of size n. Right? This is m plus n. What is 2 times n? It's taking a chain of size n and multiplying it by a chain of size 2. Which has 2 elements. So you get this. So this is m plus n, and this is 2 times n. And so I'd like you to think about this for a little bit and see why the number of linear extensions of this guy is m plus n choose m, and the number of linear extensions of this guy is the Catalan number. Okay. So, it's always nice to see the Catalan number appearing. But in this situation, maybe we shouldn't be so surprised, actually, because we know that these things are counting lattice paths somewhere, and so presumably when you try to figure out where you're counting lattice paths, you're going to get dike paths, and so that's where these numbers come from. Proposition. Let's say that you have a poset P, and look at all the maximal elements of your poset. So if P1 up to Pk are the maximal elements P. Okay. And it doesn't hurt to remind you that here maximal is different from maximum. Right? So maximum is if you had a single top element. Maximal means that there's nobody above them. So maximal in this case are these three elements. So if this is the case, then the number of linear extensions of your poset is equal to the extensions of P minus P1 plus the extensions of P minus P2 up to the extensions of P minus Pk. So it's a recurrence relation for these numbers. Yeah?
What do you mean exactly by P minus P1? Like the poset without that element?
Yeah, so I mean take the poset P and just throw out that element Pi. So like in this case, the number of extensions of P is going to be the number of extensions of this poset when I throw out 8, plus the number of extensions of this poset when I throw out this guy, plus the number of extensions of this poset when I throw out this guy. So why is this true? Given that it's such a simple statement, there should be a simple explanation, and actually there is a simple explanation, which is that when you look at a linear extension of this poset P, what's the biggest number? Who gets the number 8? The number 8 can go here, it can go here, or it can go here. That's it. Those are the three possibilities. Right? So in a linear extension, the largest number goes to some Pi. It has to go to one of the maximal elements. And if I decide that it goes in this element, then how can I complete the rest? If I force you to put 8 here, but I don't tell you where you should put the other ones, then how many ways are there to do the rest? You just have to fill out the rest of the poset, right? P minus that guy. So the largest number goes to some Pi, and it does so E of P minus Pi times. So if it goes here, then you get the extensions of this poset. If it goes here, you get the extensions of this poset. And if it goes here, you get the extensions of this poset. So that's the argument.
Do the dual minimum?
And yeah, so the exact same argument would work for the minimum. And so right, so you could say it's P minus this guy, P minus this guy, and P minus this guy. And actually, you're free to choose whichever is more convenient for you, right? So maybe if there's only 2 bottom elements and 10 top elements, then it's probably better to apply it at the bottom. Now, what I want to show you, though, is that, okay, this corresponds to, this vertex corresponds to having all of P in your order ideal. Now if I call this top element P1, P2, and P3, then actually P minus P1 lives in this picture also. Think about it. Where does P minus P1 live in this picture? P minus P1 is also an order ideal, right? Consisting of everybody except for P1, right? And so actually, when you look at this vertex, this corresponds to the order ideal P minus P1. No, P minus, I guess this contains everybody except for this guy, which is P3. So this is P minus P3. This one is P minus whom? I guess it's P minus this guy, right? So P minus P2. And this one is P minus this direction, which is P1. So actually, this recurrence is actually, it's really nice to apply in this picture. Because it says, if you want to know how many linear extensions are here, just go this plus this plus this. How do I figure this out? Well, just keep going down the poset. It's like Pascal's triangle, but in this picture instead. So let's do that. Just apply this recurrence to this picture. Okay. So if I want to find out how many linear extensions this poset has, I just start and I say, okay, let's start from the bottom and say, this guy is the empty poset. It has only one linear extension, which is not to give anybody any number. Okay, and then at each stage you just add the numbers directly below you, right? So here, 1 is below you, 1 is below you, 1 is below you. Here, 1 plus 1 is 2, 1 plus 1 is 2, 1 plus 1 is 2. Here, you get 2. Here, you get 2 plus 2 plus 2, 6. Here, 2. Is it clear what I'm doing? So at each point, I'm adding the numbers directly below. So right below, and by the way, it's always hard to to do this right on the board, so if you see me make a mistake, please help me out. So below this guy is just the 2. And you see actually this kind of thing happens in Pascal's triangle, that you just keep getting 1s along. Well, here it's almost 1s, but somehow this ruined the 1s and I gave you 2s. Here, 2 plus 6 is 8. 6 plus 2 is 8. And this is 2. Right? 2 plus 8 is 10. 8 plus 8 is 16. 8 plus 2 is 10. Then here, 10 plus 16 is 26. Here, I just get 16. Here, I get 26. Then here, okay, 26 plus 16 is 42. 26 plus 26 is 52. 26 plus 16 is 42. And then finally I add these guys, which is 136.
Is there a reason why you erased the red circle on the bottom? Around that one?
Around this one?
Yeah.
No. No, there was no reason. So you apply this kind of Pascal's-like recurrence, and you get the number of linear extensions is 136. Actually, I assigned your homework, and I asked you to choose a favorite poset, and then do this. So let me actually assign another part of the homework, which is just to figure out through this procedure how many linear extensions your poset has. So homework 2, short homework 2, part, I don't know what part B. Find the number of linear extensions of your poset. It's kind of fun. And by the way, you can imagine that if my distributed lattice is just a square grid, then you get Pascal's triangle, right? Exactly. This is just a square grid, which actually corresponds to P being 2 chains. So if P is the naturals plus the naturals, then here you're going to get just a square grid, and you're going to get exactly Pascal's triangle, which is this. Okay. Any questions about that? All right. So I think this is all I'm going to need this picture for, so I'm going to erase now over here.
Does this have a name?
This? Not really, no. I guess
Like multi.
call it like a generalized Pascal's non-triangle. Generalized Pascal's distributive lattice. No, I don't know. I don't know that there's a good name for it.
Is that 2 cross n, the poset 2 cross n, is that like a ladder?
2 times n, I just erased it. It was
Oh.
yeah, a ladder. But a ladder, not a staircase, a ladder, right? Okay. All right, so I want to define the definition. The zeta polynomial of P on a poset P is given by z of P comma n equals the number of antichains, sorry, number of multichains. Say T1, Tn minus 1. Okay. So it's this basically. But here I'm doing it in the, I realized I wrote J of L, this should be J of P. So it's exactly what I'm doing here, except you do it in the poset, not in J of the poset. You just count the number of multichains, and this is called the zeta polynomial of P. Okay. Actually, I'm going to keep this picture just in case I need it. So this was P. Yeah, so z of P comma n is just the number of ways of going up in this poset. Yes, n minus 1 elements, possibly with repetitions. Now, one thing that you should be asking yourselves is, why do you call it a polynomial? This doesn't look like a polynomial, right? It's just some counting problem. But so it turns out that it is a polynomial. In other words, there exists a polynomial such that when you evaluate it at n, when n is a positive integer, then it gives you this. And if you evaluate it elsewhere, well, that's a different question. But there is a polynomial. So this is a polynomial. This is indeed a polynomial, and one reason. So, by the way, this should remind you of if you've studied things like chromatic polynomials, it's a very similar situation. Actually, I forget, did we discuss chromatic polynomials in this class? I think maybe I mentioned them very briefly, but I didn't say a lot about them. Anyway, there's a parallel story to this with chromatic polynomials. I think we're going to get to cover it again later on. Why is this a polynomial? Let's let bi be the number of chains, not multi-chains, but chains. Okay. Now, the thing is that here I is actually bounded. Here, all the posets that we're going to consider today are finite. Okay. And so if you have a finite poset, then a chain can only be so long, right? So this is for I between 1 and however high the poset is. Okay. Height of poset. Okay? And so the thing is that if you want to have a multi-chain, then it's like a chain where you have repetitions, right? And so what you're going to do is you're just going to choose some chain, right? So, I don't know, I could be anything. Then you're going to choose some chain of size I minus 1. And then you're just going to decide, okay, how many ways are there of making a multi-chain of size n minus 1 from a chain of size I minus 1. You just have to repeat this guy a certain number of times, this guy a certain number of times, this guy a certain number of times. so that the total number is n minus 1. So then the number of ways to do that is the number of compositions of n minus 1 into I minus 1 parts. This is the number of ways of turning this chain into a multi-chain through repetitions. Okay? We know the number of compositions. We've enumerated this, so we get this. Okay, and then the thing is that this thing, as a function of n, this is polynomial in n. Right? If I is some number like 5, then n minus 2 choose 3 is a cubic polynomial. In general, it's a polynomial in n of degree I minus 2. Okay? And because this is a finite sum from I equals 1 to the height of the poset, then it's a finite sum of polynomials, and therefore it's polynomial. Okay? Yeah?
I forgot what a multi-chain is.
A multi-chain is a chain where you can repeat elements, right? So a chain is that you go here, then here, then here. And a multi-chain is to say go here, then you stay there, then you stay there, then you go up, then you stay there, then you go up, then you stay there, then you stay there. Just a chain where you are allowed to repeat things, and that's why I get this extra factor. But so this shows that this is a polynomial. And of course, it's a polynomial related to this stuff, right? Now, there's another polynomial that I want to define, which is the order polynomial. And this is going to be the number of order preserving maps from P to the chain size n. Okay. So again, it's what we just studied. Now I'm giving it a name. I'm calling it the order polynomial. Now, why do I call it a polynomial? How do I prove that this is a polynomial? Well, because this is, by that theorem, right? This is the same thing as the zeta polynomial of the distributive lattice at n plus 1. Right? If I consider one of these guys, right? The order polynomial counts this, but that's the same as this. And so these are the multi-chains in J of P, actually of size. They start at I1 and they end at IM minus 1. The start and the beginning here are not really important. And so because I proved that the zeta polynomial is polynomial, then I get that the order polynomial is also polynomial. Okay? So that's that. Now, can you tell me what the degree and leading coefficient are of this thing? Just need to change this thing here. So the degree of this thing is the degree of this thing, which is basically how high you can go in your poset. Right? It's the height of the poset, but it's not the height of P, it's the height of J of P. How high is this poset? was you start with the empty order ideal, you end with the full order ideal. So the height is the number of elements. And what is the leading coefficient? It's this number for when I is as big as possible, right? So it's the number of maximal chains of J of P. So this is, you're going to get an E of P here, right? Because the maximal chains of this poset are precisely the linear extensions. And actually, n choose I comes with a division by I factorial. And so you end up getting this actually. So you can do it more carefully than I'm doing right now, and you'll see that this is the leading coefficient. And so you see that this is this order polynomial is a polynomial that if you happen to know it, then you also know how to enumerate linear extensions. But it's a lot more information.
Is the height that minus 2 or just that?
The question is, why did I write this instead of the minus 2? And the answer is that it has to do with this 0 and 1 over here. And I think I'm a little bit careful. I was a little bit careless when I dropped them. And if I was more careful, I would have seen that it's P and not P minus 2. So your worry is valid, I agree. But this is, when you think about it carefully, you get this. Okay. So what I want to do next is bring in a little bit of algebra and show how some of these things actually appear very naturally from an algebraic point of view. So what I want to do is that I want to talk about the incidence algebra of the poset. Okay. Those of you that took half algebras with me, this will be a familiar notion that actually appears very naturally in the context of half algebras, but we're not really going to need any knowledge of combinatorial half algebras. We're just going to go straight from the algebra. Okay? So the incidence algebra of a poset P consists of the real algebra of, and I'll remind you what this means in a second, or maybe tell you what this means if you haven't seen this before. It basically consists of the functions from the intervals of P to, let's say, R. Okay, and if you want to put something more general than the reals, you can do that if you want. Okay, but we're just going to consider functions from the intervals of P. Okay, so int P represents the intervals x comma y such that x is less than or equal to y in P. So the incidence algebra just consists of doing the following thing for let's say raise j of P. We don't really need it anymore. And we're just looking at P. And so the incidence algebra consists of all the ways of taking each interval over here for every element less than another element, you assign some real number. So this is really kind of like R to the intervals of P, right? You just choose a number for each interval. Okay. Now, what is an R algebra? It's something that is a vector space. So why is this a vector space? Because we're just going to allow ourselves to add functions. So if you have a function from this to this, and you have another one, then there's a very, very clear way of adding them, which is just to add the corresponding numbers. And also you can multiply by scalars. Okay? But it's also a ring. Meaning that you have also a multiplication operation, which I need to tell you what it is. So what's the multiplication? Of two functions. So to define the multiplication f of g, f times g, I need to define it on every interval, right? And so I say, what is it on the interval x comma y? And what I'm going to do is something that is very common in several parts of mathematics. I'm going to take the convolution. F of something, g of something. Okay. And the usual way to do this should be x something and something y. That's the way convolution works. Okay. Now, what am I summing over? I'm summing over all the possible values of z. And where can z be? So z needs to be bigger than x for this to be defined. And z needs to be less than y for this to be defined. So this is convolution. Okay. And it's very easy to check that this satisfies all the axioms, and this, for example, this multiplication is, what's the word I'm looking for? Associative, right? F times G times H is going to be the same no matter how you put the parentheses. And you can check that it's compatible with the vector space. The usual stuff that you can check. This all works out, okay? And so if you're not too familiar with this stuff, you should just think, okay, we're considering these functions that I was discussing here, and we're just allowing ourselves to add them, to multiply them by scalars, and to take products of functions through this recipe. Okay. Now I claim that this is that this ring. Well, so what can we say about this ring? For example, one thing that you should realize is that this ring is probably not commutative. Because why should it be, right? If you do g times f, then you get g here and f here. Maybe it's worth keeping a picture in mind, which is that here I'm thinking, okay, what number should I assign to the interval from x to y? And here what we're doing is we're saying, take the interval from x to y, and then take a z in it, and then just see what did f assign to this interval, and what did g assign to this interval. And as you sum over all the values of z in this interval, you're going to get whatever fg assigns here. Okay. And so from this picture, it should be clear that this is not at all symmetric in G and F. Right? So this is probably not a commutative ring. Does it have a 1? It's not even obvious if it has a 1, right? I mean, this happens a lot in combinatorics. We define these rings, and then they just can be really weird sometimes. And so you have to kind of start from scratch and say, okay, does this ring satisfy some of the very basic properties? Well, it turns out that this ring does have a 1. Multiplicative identity. It's called 1. Okay, but it's not the number 1, it's the function 1, which assigns to the interval xy 1 if x and y are equal, and 0 if x is less than y. And why is this? Because you imagine that g is 1, okay? So what is g doing? G is saying, okay, if this interval is not trivial, then I put a 0, so that doesn't contribute anything. This only contributes if this interval is trivial. And if this interval is trivial, then this guy is up here, and then I'm just applying f to all of xy. So that's why fg is going to be equal to f when g is equal to this thing. And similarly, I mean, it's multiplicative identity on both sides. All right, so why do I bring this up? Because actually, this thing, the zeta polynomial appears very naturally from this point of view. If we define the zeta function of p to be, so that's my best effort at a zeta. This is the function that to every interval assigns the number 1. Okay? It's a little bit strange. I mean, this sounds more like this should be called 1. Right? This looks more like a 1 than that one. But you shouldn't confuse them. The reason that we call this one 1 is that this is the multiplicative identity in the ring. And because this one is not the multiplicative identity, we shouldn't call it 1, or we're going to get confused. Okay? So we call it zeta. For all x less than or equal to y. Okay? And so, what happens when we compute, for example, the function zeta squared? And by the way, one thing that we start doing after a while is that we get tired of drawing the square brackets and we just do this. Okay, and you understand that that's an input. So what is zeta squared of xy? Well, by definition, this is the sum x less than or equal to z less than or equal to y, zeta of x z, zeta of zy. Okay? And that looks ugly, but it's very simple actually, because this is always 1. Right? So this is just the number 1. Okay? So then what is this? Well, it's the sum over the z between x and y of the number 1. And so you're just taking the number 1 and adding it, the number of elements in the interval from x to y. Okay? Which is already kind of powerful because often, often counting the number of elements of a poset is very useful. Right? Like if we manage to count the number of elements of J of P, then we'll know the number of linear extensions of the poset. Even counting elements of a poset can be non-trivial, and this gives us an algebraic approach. It's just the zeta function squared. But let's take it a step further. What if I take the zeta function to the n? Okay. Then I'm gonna get like an nth convolution, right? So this is gonna look like this. I get this, and then I get zeta of x z1, zeta of z1 z2, etc. up until zeta of zn minus 1 y. And again, even though this looks very ugly, it's extremely simple because all of these are ones. How many ones? The number of ones is exactly the number of multichains between x and y, right? So this is actually just the zeta polynomial of, this is the number of n multichains from x to y. In other words, this is the zeta polynomial of the interval xy. So that's a nice statement that if we're interested in zeta polynomials, then the zeta polynomial is actually just the nth power of the zeta function. Okay? And the zeta, I mean, one nice thing is that the zeta function was as simple as could be, right? This is just the simplest function that you can think of on the poset, and just by taking powers of it, you get this one that we're interested in. Okay, so this is, and this is why these two have the same name, right? Zeta, zeta.
Are there any other interesting functions from the incidence algebra that gives you interesting polynomials?
Yeah, so let's what other functions can we define? Let's one thing that we can ask is, okay, well, you know, you have a ring. This ring has a multiplicative identity. So can we take inverses, for example? And you know that in a ring, usually you can't just take inverses. You need to check who's invertible, who's not invertible, right? So who's invertible here? Well, that's an algebra exercise. You just have to kind of get your hands dirty in the ring, try to invert an element, and see if you can. Then when you do that, you're going to find that an element is invertible. So f is invertible in the incidence algebra. I didn't give a name to this. The incidence algebra I of P. So what are the invertible elements? If and only if f of xx is never 0. Okay. Again, this is not obvious. You have to kind of try to invert an element, and you'll see that you're just forced to divide by f of xx. And if that number is not 0, then you're able to invert your function. Okay. So you can see the proof in the book. It's not hard. You really just have to get your hands dirty and invert an element. Now, since the zeta function is always equal to 1, that means that it's invertible, right? Because it satisfies this property. So maybe a next function that we should consider is the inverse of this thing, the inverse of our simplest function, right? And we call this function mu. called the Möbius function of the poset. Now this might surprise you because I know that some of you guys have thought about Möbius functions before, and maybe this is not how you expected the Möbius function to come up, but this is the same Möbius function that you're used to. This is the same Möbius function that you're used to, and an equivalent definition is the following. Mu of xy is equal to 1 if x is equal to y, or if x is less than y, then you get minus the sum x less than or equal to z less than y of mu of x z. And we'll do an example, but for now I just want to point out that this is the same thing as this, because you see, this case is kind of trivial. Really, the meat is here. This is the important thing. If x is less than y, then what am I saying? This is equivalent to saying that the sum, I mean, here I'm just omitting the term where z is equal to y, and that's this term. So if I send this one over, I'm going to get this, right? And I might as well put zeta here, because zeta is equal to 1. Okay? Zeta of anything is equal to 1. And so here what I'm saying is that the convolution of mu and zeta is 0 when x is less than y. And then you can easily check that when x is equal to y, you just get that it's 1. And so this is saying that mu times zeta is 1. So this is the more usual definition, but it's equivalent to this equation. And there's advantages to doing things algebraic. For example, one advantage of doing things algebraically is that I get a very simple proof of a very important theorem, which is the Möbius inversion formula. Which says the following: let P be a poset, let f and g be functions from the poset to maybe the reals or maybe some other ring, it doesn't really matter. If you have that g of, let's see what notation did I use here. Okay, I don't like that notation, let's use this. G of y is equal to the sum of x over x less than or equal to y of f of x. Then, so if you express g in terms of f like this, then the way of expressing f in terms of g is almost the same. You're just supposed to put a Möbius function. And I know that I'm doing this too quickly at the moment, but what I want to do is for now I'm going to ask you to trust me that this is an extremely important theorem. And in the next few classes, we're going to spend a while seeing exactly how you compute this Möbius function, exactly what this means. But you'll see that this theorem is extremely useful all over combinatorics. And what I wanted to do is just give you a very quick algebraic proof, okay? And once it's proved, then we'll see better what it actually means. Okay? Actually, since we're being algebraic, let me just do something algebraic. Consider the functions from P to the rings. Okay, so this is where these guys live. Okay. And then I'm going to say that the incidence algebra, rather, before I write a word that is going to scare half of the people in this class, let me say two things. One, there's a completely elementary proof in the notes. And I wasn't planning to do this, but I actually want to do it now. So if you happen to know about rings and modules, then this is going to work. And if you've never seen them before, actually just the manipulation I think will sound reasonable to you. So M is a module over my ring of my incidence algebra by. So what does it mean? It means that I can take an element of the incidence algebra and make it act on, so I shouldn't call it F, right, because I want to call F the thing in M. Okay, so I don't know, let's call this A. Okay, so A is in the incidence algebra, F is in the module, and so what I should get is something in the module. In other words, I should get a function from P to R. Okay? And this should be, so because if it's a function from P to R, I need to tell you how to evaluate it on an element of P. Okay? And it's going to be kind of the natural thing. And so I guess actually I want to say that this is a left module. So I should. It's a left module. So okay. So I claim that this is a module over the ring, and again, you kind of have to sit down and check the axioms, make sure that this works out. It does work out. And then once I say this, actually this proof is completely, I don't want to say completely trivial, but it's really very simple. What is this equation saying? Well, let me put A equal to mu, to zeta, right? So what I'm saying is that when F when I put F and zeta here, then this is going to be 1. And so I get that F times zeta is this, which is G. Right? So that's the blue equation. Now what's the red equation?
Oh, yeah,
The red equation says that f is equal to, now if I put g here and mu here. Right? And then it's completely clear that these two things are equivalent because sigma is mu inverse, right? And so if you have this equation, then multiply by sigma inverse, which is mu, and you're going to get that g times mu is f. So to get from here to here, you just write multiply by sigma inverse, which is mu. Okay. So that's it. That's the proof. And like I said, it's not hard to give an elementary proof, and there is one written here. But I wanted to show you this one so that you see that if you set up the algebraic framework, it's just kind of for free. You don't have to do any work. Well, the work is understanding the algebraic framework, but once it's in place, it's a very trivial computation. Okay. So like I said, in the next few classes, actually, as I told you over email, so next week is Thanksgiving. Instead of lecturing, I'm having you watch some classes from a previous course where I taught Möbius functions and Möbius inversion, not from the algebraic point of view. Okay? And also I taught a little bit about hyperplane arrangements. And so you'll see a completely elementary presentation of what I just did. And then when we come back, we're going to do a lot of applications of this stuff. Okay? But I wanted to show you this theorem. And maybe to conclude, I just want to show you a quick example of what a Möbius function looks like, so that we at least see one. I shouldn't have erased this, so. So let's look at the positive divisors of 84, I think is the number that we had. 84 is 7 times 12, yeah. So this looked like hold on. So it looked like a box on top of another box. We did this example. And we got this poset. So let me at least show you how to compute mu of bottom element, comma, 1. So we're not going to compute mu of x, y for every interval. We're only going to compute it from mu from the bottom to each y. So what does this say? It says, okay, first, if x is equal to y, put a 1. And if x is not equal to y, then at each point, you just look at the numbers below it, you add them, and you put a minus sign. So below this guy is a 1, and you change the sign, you get minus 1. Similarly here, similarly here. Below this guy, and I mean below in the poset, right? Not by levels, but less than in the poset. So less than in the poset, I have these 3 guys. They add up to minus 1, and if I flip the sign, I get a 1. Similarly, below this guy, I have minus 1, and 1, so I get a 1. And below this guy, I have a minus 1 and a 1, so I get a 0. Okay. What about here? Minus 1, and 1, I get a 1. Below this guy, I get 3 1s, 3 minus 1s, and a 1. They add up to 1, so I change the sign and I get minus 1. Below this guy, I have 1, minus 1, and 1. That adds up to 0. And And below this guy, I get these 4 guys that add up to 0. And finally, below this guy, I have minus 1, 3 1s, 3 minus 1s, and a 1. So these blue numbers that I wrote here are the numbers mu of 0, comma y, where 0 means the bottom. If you want to compute mu of xy for some other x, like for this x, then you would just start here and you would say, okay, mu of xx is 1, and then you would just look at that part of the poset and do the same thing. So if this is 0, you do this. If this is x, you do the same thing, but starting at x. So you see, actually, the Möbius function is, it's a, at least for a small poset, it's a very manual procedure that you can do, and it's equivalent to the simple algebraic differential. Okay, so I think that's a good place to stop, and you guys have a great break, and we'll see you in a little over a week.